Hello, my name is Caden Bunch. This is my presentation on the G542X and F508del mutations of cystic fibrosis. So some of y'all, if you've grown up in Utah, you've noticed this is a pretty close-knit community in which you may share the same grandparents often. And then although this is great for social interactions, it's not so great when it comes to these human genetic diseases that can pass through families. So one of such of these diseases is cystic fibrosis, which is characterized by mutations in the CFTR gene, or the cystic fibrosis transmembrane conductance regulator gene. And when there's issues in this gene, it causes extreme thickening of mucus all along the lungs and intestines. And although there's many mutations responsible for this, we found that G542X and F508del mutations are the most common in those impacted. So as you can imagine, you can't really study these diseases in humans because you can't really get inside of humans and look at their organs. It's quite a hassle, you can imagine. So what we got to do is we got to create animal models in order to study these diseases and help work out if we can cure it in a speedy manner. So what we've done here is we've implanted these sheep with cystic fibrosis, and we found that they have extreme phenotypic displays. That we see symptoms in them extremely strongly. One such being meconium ileus, which is basically when you're so constipated that it leads to death. We've also found that cystic fibrosis doesn't only cause thickening of mucus, but also causes hinderment in the development of the fetus. So what we've done is we use CRISPR-Cas9 technologies in order to correct this mutation, and we were successfully able to do so. We see that on this bottom right here. However, our biggest issue was it has pretty low efficiency. We can see that high percentage of indels being insertion deletion mutations, basically adding or taking away nucleotides in the genome. And as you can imagine, that kind of causes a lot of issues. So we wanted to increase that. We wanted to reduce that. We wanted to make it more efficient. And that's where this PiggyBac transposon comes in. So as some of you all may know, transposons are called jumping genes. And what they basically allow us to do is they allow us to put a gene into a certain location. And our hope is to use this to put in the correct functioning CFTR gene and take out that mutated one. And then what PiggyBac does is when it inserts and when it exits, there is no indels. It's a clean excision is what we call it. And right now we're constructing a vector to kind of display this in order to express it and try it out in bacterial colonies in these coming weeks. So what we found is we can effectively cure these diseases using CRISPR-Cas9 technologies. However, we want to increase efficiency. We want to make it less risky. We want to get rid of those indels. And through the use of the PiggyBac and prime editing, another genome editing technology, we hope that both of these can show potential to be more accurate than CRISPR-Cas9. So our work shows promise. We want to help. We show promise of curing these genetic diseases. It's possible. We just got to fine tune it. We got to increase the efficiency for it to be an effective tool for correcting genetic diseases. Thank you.